Okay, we want to now start to apply the concept of conservation of momentum to the subject of collisions, and this is where the conservation of momentum is most easily and readily applied at the introductory level. So collisions come in two essential flavors. Now there's actually a very broad spectrum in between these two, and I'm going to caveat this with I don't want to necessarily write out the word perfectly inelastic and perfectly elastic all the time. So anytime I use the terms inelastic or elastic, we're going to assume that we're talking about a perfectly inelastic collision or a perfectly elastic collision. And I'll explain what all that means here in just a moment. So inelastic collisions have the defining characteristic that momentum is conserved. Momentum is always conserved for systems that where the net external force is zero, and that is very important to stress. We're not talking about systems that are subject to outside forces, only systems where the forces we're taking into account are when the objects exert forces on each other. Okay, and in an inelastic collision, P is always conserved, but kinetic energy is not conserved. Okay? In inelastic collisions, momentum is always conserved, kinetic energy is not conserved. Now, we contrast that with elastic collisions, and in that case, we have the condition that momentum is conserved and kinetic energy is conserved. More precisely, some people use the word constant. The kinetic energy stays constant throughout the entire process. Either way, at least at our level, the two definitions or the two statements are essentially the same thing. Now, behaviorally, what does this mean? So the difference between a truly elastic collision and a truly inelastic collision is that in an inelastic collision, the objects will bounce off of each other. Okay? Now, in the macroscopic realm, you never have a truly elastic collision. Anytime objects bounce off of each other at the macroscopic level, you're always going to get some sound, you're going to generate some heat, and some of the mechanical energy may or may not be turned into internal energy thermodynamically. But there are systems that are essentially elastic. We've already talked about the billiard balls, when, especially at low velocities, when you have one ball rolling across the table and they collide, then that collision is often very well modeled, very well approximated by elastic collisions. So the elastic collision cases where your objects bounce off of each other. Now this is fairly complicated, or can get complicated, because you're dealing with potentially two objects, and we're going to restrict our discussion to two objects. You essentially have two objects that may have their own initial velocities, so they may be moving in different directions. And then when they bounce off of each other, they're also both going to be moving in different directions. So assuming that no mass is lost or transferred from one object to another throughout the system, at least our masses are constant, but we still have to worry about potentially two initial directions and velocities and two final velocities, and the associated directions, the angles that each velocity has associated with them. So elastic collisions, even only among two objects, can get very complicated very quickly. And we'll see why here when we actually start doing the examples. But that is the characteristic of an elastic collision. Momentum is conserved, kinetic energy is conserved, and the objects tend to bounce off of each other. Another very good example of an elastic collision may be like a rubber super bouncy ball, and you throw that rubber bouncy ball against the wall. It doesn't generate a lot of noise typically, and the ball will bounce off of the wall with essentially the same speed that it hit the ball with, and thus very little kinetic energy was lost. Okay, so those are a couple of examples of macroscopic elastic collisions, or things that can be easily modeled with elastic collisions. Inelastic collisions, of course, have the condition that momentum is conserved, kinetic energy is not conserved, and under the condition of inelastic collisions, the objects tend to stick together. They don't bounce off of each other, they collide and they will stick. And this makes the mathematical analysis a lot simpler. So that's the example that we will do first, and then we'll look at the elastic case. All right. So in the inelastic case, the objects bounce off. Or I'm sorry, they stick together in this case. Whoops. The objects stick together. Okay, so this gives us a good working definition between both types of collisions. Okay, elastic, kinetic energy is constant, the objects bounce off of each other. Inelastic, the kinetic energy is not constant, and the objects stick together. Okay, so now let's do a simple example with a inelastic. Let's do inelastic first. Let's do a simple example with an inelastic collision. So the classic question that we ask with inelastic collisions is, if I know the speeds and masses of both objects before a collision, what is going to be their final speed after the collision? And the way we do this is we set up the conservation of momentum in equation form, and then look at the momenta of both objects before the collision, and we know that the sum of those momenta must be the sum of the momenta after the collision. So let's start with a very simple example, and let's look at two carts. And we will, for starters, assume that both carts have the same mass. So assume that both carts have a mass of m, right? And we'll call this cart 2, and we'll call this cart 1, and we'll say that this cart is moving with some initial velocity v, and this cart is stationary. Right? So these two carts are on our track. Cart 1 is moving with a speed v, and cart 2 is stationary. So we have this kind of system. All right? And they both are outfitted with Velcro on the end. And so here's the little spiky Velcro, here's the fuzzy Velcro, and this will cause the carts to stick together after the collision. Now obviously if this guy is just sitting on the track and this cart is moving this way and they collide and stick together, they're going to continue moving in the original direction. But with what speed? So that is the classic question. So the question that we want to ask is, what is the final speed of our system here? Okay, what is the final speed of our system? Now I'm going to have to erase the picture for room on the board, but you'll get the idea here in just a moment. So keep this picture in your head. All right, keep the picture in your head. So here's where we start. All right, here's where we start to solve this problem, and I always start by writing down this equation. And this equation is simply a modified form of the conservation of momentum. And what it says is that the initial momentum in my system must equal the final momentum in my system. In other words, the momentum in my system before the collision must equal the momentum in my system after the collision. So before the collision, how much momentum do I have? Well, I have the momentum wrapped up with my first object as it's moving. So the first object is moving with an initial speed v and has a mass m, so the total initial momentum in my system is just mv. And then after the collision, what momentum am I going to have? Well, after the collision, they stick together and they're both moving, but they move off with some common final velocity. And the masses are now added together. So the total final momentum of my system is the total mass that's moving and the total final velocity that the objects are moving together with. So this is going to be the mass of cart 1 plus the mass of cart 2 times the final velocity that they're moving with. And remember what our question was. I want to know what the final speed the system is moving with, and so this is the variable that I'm solving for. I want to know what my final speed of the system is. So we can solve this by adding our two m's together, and this becomes 2m times Vf. My masses can then cancel, and I find that my initial velocity is equal to twice my final velocity, or my final velocity is just 1/2 of my original velocity. And this shouldn't come as too much of a surprise. Most of us have an intuitive idea that this is what would actually happen. If I have two equal masses and one comes in at some velocity and they collide and stick together and they start to move off, then they will move off at half the speed. And that is indeed what we find. Now, how would I change this problem if the second cart were actually moving toward the first? All right, I'll let you think about that one. We'll do that in the next video.